Welcome to the section on typical wastewater characteristics. I am Paula Carrera, a postdoctoral researcher at Ghent University, working in the group of Professor Evelyn Volke, and I will guide you through different aspects that are related to the characteristics of the wastewater. If you want to know more details about this, you can check the reference in the slide, in particular the section 11 of the chapter 3 of the Biological Wastewater Treatment book, Principles, Modeling and Design. Here we will learn about population equivalence, municipal wastewater composition, ratios and dynamics, and we will also dive into different streams that play a role in the wastewater treatment plants, including external inputs such as domestic and non-domestic streams and internal loads. And we will also dive into non-sewer sanitation flows. Let's start with population equivalent. The population equivalent, or per capita, is a standard unit referring to the typical contribution of one individual to the wastewater load. We can use this parameter to have an idea on the loading of the wastewater treatment plant. The population equivalent can be expressed based on different parameters. For example, we can express it in terms of flow, from which one population equivalent is equal to 0.2 cubic meter per day. And we can also express it, for example, in terms of organic load. And for this, we can use an equivalent of 60 grams of BOD per day as one population equivalent. These two definitions are based on fixed values, which are independent of the volume of wastewater that is being produced per person and per day, or the source of the wastewater. And they can be used to take into account the contribution both from cities or towns and also the load coming from industrial streams. Another way to express the wastewater load in a sewer catchment is the person load. It represents the actual contribution to the wastewater production from a person living in a sewer catchment. This parameter is different from the population equivalent and can actually change considerably. The reasons that explain these changes can be related to the location of the working places, socioeconomic factors, lifestyle, or the type of household installation. The person load can be expressed based on different wastewater characteristics, such as organics. We can express it, for example, in terms of BOD or COD. But we can also express it based on nutrients, such as nitrogen and phosphorus. And we can also express it as well based on flow rate, for example. The person load can also change from country to country, and here you have a figure to illustrate this. In general, we have higher person load for pollutants with higher concentrations in the wastewater, and this is why, for example, BOD or TSS have higher concentrations compared to the nutrients. We can see in the figure, for example, that the European countries, such as Denmark and Germany, have similar numbers for all the pollutants. And the US is also close to the European values, but with higher values for some variables, such as the BOD person load. Other countries, such as Egypt, India, and Turkey, have values that are close to each other and lower than the previous countries. And then we have Brazil, for example, that is something in between all of them. It is important to remark at this point that these two options presented, the population equivalent and the person load, are often confused, but they should be carefully used. They are both based on average contributions and used to give an impression of the loading of the wastewater treatment processes. However, there's a main difference between the two of them, that is that the population equivalent is based on one fixed value, whereas the person load changes depending on the specific place. Let's do now a small exercise to put into practice what we have just learned. So imagine that we live in an island with 240 people and we collect all the generated wastewater. We know that the daily amount that is being produced is 60 cubic meters per day, and we also know the associated organic load, which is 18 kilograms of BOD per day. Based on this, we have to calculate the person load in terms of flow and in terms of BOD. Let's start with the calculations for the flow. The value that is provided in the exercise basically refers to the total flow. This means the wastewater flow produced by the whole population. So what we have to do is to transform this value into something that is specific for one person. And to do this, we basically have to divide the total flow that is being produced by the number of people that live in the island. And in this case, we get a value of 0.25 cubic meter per person and per day. Let's go now to the calculations for the BOD person load. Here, the principle behind the calculation is the same as before. We know how much is the total amount of BOD load that is being produced, and we have to divide it by the number of people that live in the island. And this way, we can calculate a person load of 75 grams of BOD per person and per day. If we go back now to the description of the exercise, we have calculated both the flow and the BOD person load with the provided information, which includes the total flow and the organic load that are being generated. Let's move now into the next part of this section, in which we will talk about municipal wastewater composition. The wastewater composition, defined by the concentrations of different pollutants, depends on the pollutant load and also on the amount of water in which the pollutant is being mixed. The amount and composition of the produced wastewater differs between humans and also among industries. And the main influencing factors that explain these differences are the behavior, the lifestyle, and the standard of living of the inhabitants, as well as the technical and theoretical framework in which people live. And of course, the composition of the municipal wastewater changes significantly from one location to another, and it will also change over time as well. The differences in composition will depend not only on the consumption habits, so what we have just discussed, but also on the specific location of the households and also the retention time in the sewer. And other processes, such as infiltration and exfiltration of water during transport, will also affect the composition. In these figures, you can see examples of wastewater composition corresponding to typical municipal wastewater with minor contributions of industrial wastewater. We can see, on the one hand, high concentrations corresponding to cases in which there's low water consumption or low infiltration, and that's why the concentrations are high. And we also have values of medium and low wastewater concentrations, in which there's a higher water consumption and infiltration, and thus the pollutants concentrations are lower. Here it is important to also take into account the contribution of stormwater, since it can dilute the wastewater, because most of the stormwater components have much lower concentrations compared to even very diluted wastewater. So let's now take a look at the compounds more in detail. The organic compounds concentrations can oscillate between 500 and 1,200 grams per cubic meter. We can see that the organic compounds are divided into different fractions, as explained in the previous parts of this chapter. We have, on the one hand, a fraction that is suspended or particulate, which can suppose up to a 60% of the total COD. The rest corresponds to the soluble fraction. And here it is interesting to characterize, for example, the volatile fatty acids BFA concentration, since it is the easiest compound to be degraded by bacteria and is key for some processes such as phosphorus removal. However, BFAs usually suppose a small fraction of the soluble COD. If we look now at the total suspended solids, we see that the concentrations can oscillate between 200–600 grams per cubic meter. They can be further divided into volatile suspended solids, VSS, and inert suspended solids, ISS. Normally, a big fraction of the TSS will be in the form of VSS, while the rest is inert. Here you can see what would be the associated nutrients concentrations. Again, we have different values depending on the water consumption and infiltration in the sewer. If we look first at the nitrogen concentrations, we see that they can oscillate between 20 and 100 grams per cubic meter. Nitrogen compounds include ammonia, which is usually the main fraction and can represent between 60–70% of the total nitrogen concentrations. Then the rest is usually in the form of organic nitrogen. Normally, nitrite and nitrate concentrations are very small, so they can be considered negligible compared to ammonia and organic nitrogen. Phosphorus compounds can oscillate between 5 and 25 grams per cubic meter. The total phosphorus is usually constituted by an inorganic fraction, the orthophosphate, and an organic fraction. Orthophosphate usually supposes a 60–70% of the total phosphorus, while the rest is organic phosphorus. Treatment processes are based on biological degradation and conversions of substances, so it is also important to have an idea of what is the biodegradability of the wastewater. In this slide, you can see some examples of what are the typical biodegradable and unbiodegradable fractions of the wastewater. Total COD, for example, can contain up to 80% of biodegradable COD, while the rest should be unbiodegradable. And something similar occurs for total nitrogen. Total phosphorus can have a higher biodegradable fraction, up to 98%. And BOD, on the other hand, will always be completely biodegradable. Let's move now into another topic, which is the importance of the ratios in the wastewater. The ratio between various components in wastewater has a big influence on the selection and the operation of the wastewater treatment processes. One example of a useful ratio is the COD to BOD ratio. We know that if this value is too high, there will be difficulties for the biological processes to remove organics from the wastewater, since we will have a low biodegradable fraction. Another example is the COD to nitrogen ratio. We know that if the value is too low, there will be probably carbon source limitations for denitrification, and thus low nitrogen removal efficiencies in the plant. We can use this ratio as a way to identify, for example, if we need to add an external carbon source to ensure good nitrogen removal. Another example of a useful ratio is the VFA, volatile fatty acids, to COD ratio. If this ratio is too low, that means that we will have problems with phosphorus removal, since the bacteria responsible for it are able to metabolize only VFAs. Another example is the VSS to TSS ratio. A high value indicates a high organic fraction of the suspended solids, and this can be successfully digested under anaerobic conditions. These ratios typically remain relatively constant, and their analysis throughout time can help us identify anomalies in the wastewater. If we see, for example, that the values change, this could mean that there are errors in the analysis performed to the samples of the wastewater that we collect. Or there could be, for example, special discharges into the sewer that often come from industry. In this table, you have an example of the typical ratios that should be observed in municipal wastewater. And again, we have values for low, medium, and high wastewater concentrations. As mentioned before, we can have different values depending on the load of the wastewater, but normally, the higher the load, the higher the ratios. Let's do now another exercise to put into practice what we have just learned about this topic. Imagine that we work in a wastewater treatment plant and we have to treat a certain wastewater with the composition that you can see in this slide. We have to calculate different ratios and interpret their values. That means we have to see what we can infer from them. To calculate the ratios, we just have to divide the corresponding variables that are indicated by each ratio. For example, for the first one, we divide the COD by the BOD concentration. And here you can see what the results of the calculations could be, as well as the reasonable ranges that were shown before. So let's take a look now at the values. If we start with the COD to BOD ratio, we can see that the calculated value is considerably lower than the reasonable range. In addition, if the ratio is lower than 1, this indicates that the BOD concentration is higher than the COD. But this should never be the case, since it's always the opposite. And this already indicates that probably one of the two analyses must be wrong. So we have seen that the COD to BOD ratio is unusually low, and the same happens with the COD to total nitrogen ratio. Again, the value is below the typical ranges. If we analyze now the BOD to total nitrogen ratio, we can see that it is high, but within the expected range. And this indicates that the BOD value that has been measured is probably correct, and there's probably an analytical error in the COD measurement. If we take a look now at the COD to VSS ratio, we can see again that it is extremely low and also below the reasonable range for wastewater. Finally, if we take a look at the VSS to TSS ratio, we see that it is medium-high, but within the expected range. So, after taking a look at all the ratios together, we can clearly see that those related to COD are always extremely low, and as mentioned before, we even have a COD to BOD ratio below than 1. And all of this clearly indicates that there must be something wrong with the COD measurement. Let's go now to the section on domestic wastewater substreams. The wastewater consists of different subflows. That means different water streams that will be mixed together and treated in the plant. Each stream contains specific amounts of organic compounds and nutrients, and the composition of the wastewater can change if the amount and composition of each substream changes. Two streams constitute the external inputs of a wastewater treatment plant: the domestic and the non-domestic sewage. These streams are generated outside the plant, discharged into the sewer, and then sent and treated in the treatment plant. There are also internal inputs, which means wastewater streams that are produced inside the treatment plants and will be also part of the load that the plant needs to handle. Now we are going to take a closer look at the domestic sewage that is one of the external inputs. And for this, we have to see what are the different substreams that constitute the domestic wastewater that comes from the households. Here we can identify three sources of household wastewater. The first one is the water coming from the toilets. From this stream, urine is the main contributor to the nutrients loads in household wastewater, and more specifically nitrogen. For instance, up to 80% of the nitrogen that is present in domestic wastewater is due to the nitrogen that comes from urine. The second source of wastewater in a household comes from the kitchen, and it includes kitchen waste that normally has a significant amount of organic matter, and gray wastewater, which might contain household chemicals. The third source of household wastewater comes from laundry, bathing, and showering wastewater, and this normally supposes a minor pollutant loading compared to the other two sources. Here you can see what are the typical yearly contributions of each stream expressed as mass flows. We can see that all the streams have similar volumetric flows, but significantly different contributions for the different components. So let's take a closer look. In terms of organics, the toilet is the main contributor to the COD load, followed by the kitchen, and then the bath and laundry have a much lower contribution compared to the other two. If we observe the BOD profiles, we can see a low BOD load for the toilet with respect to the high COD value that we have just seen. And this indicates that a big fraction of it is not biodegradable. On the other hand, the kitchen waste has higher BOD flows and also closer to the values for COD, which indicates that a big fraction of the kitchen wastewater is actually biodegradable. If we look now at the nutrients load, the toilet is the major contributor, especially for the case of nitrogen. And if we take a closer look to the toilet stream, we can see that urine is the main contributor for the nutrients load. It also supposes more than half of the volumetric flow from this stream. However, only a small fraction of the organics is due to the urine. Normally, the wastewater produced by all the domestic streams is mixed together and sent to the treatment plant. However, there are also options to treat each stream separately and that way change the load that will be handled by the treatment plant. For example, we can treat urine separately, and that way we can considerably reduce the nutrients load in the treatment plant to the point where nitrogen removal wouldn't even be needed. Another option could be to transfer the kitchen waste into the solid waste fraction instead of the water fraction. And this way we can reduce the organic load that will go to the wastewater treatment plants. The generated gray wastewater can be reused for irrigation or for toilet flushing, but we need to treat it first. And the same happens with the water coming from laundry, bathing, and showering. It can be used alone or together with the kitchen wastewater for the same purposes. All these options aim to reduce the load applied to the wastewater treatment plant and could be useful in case that our load is too high and we want to reduce it. But we can also do the opposite. We could, for example, install waste grinders in the households, and this way we could increase the organic load. Let's go back now to the scheme of the sewer and the treatment plant. We are focusing now on the external inputs, and we have just dived into the different domestic substreams. Let's see now what are the sources for non-domestic sewage, which are also part of the external inputs. This term refers to all the wastewater streams not produced by the households that will also be treated in the treatment plant. We have two main non-domestic contributors: wastewater that comes from industries that do not have a treatment facility, and other external inputs such as landfill leaching. Wastewater coming from industry usually presents wide variations in composition, and it's fully dependent on the type of industry. In addition, it normally presents fluctuations over time due to the dynamic operation of the factories. This table shows examples of the typical composition of different industrial wastewaters. As you can see, the concentrations of all the pollutants are in general much higher than those from domestic wastewater, and the values are highly dependent on the type of industry. If we take a look now at the organic concentrations, we can see that they can oscillate between a few grams per cubic meter to almost 100,000 grams per cubic meter. The BOD concentrations usually suppose maximum around 50–60% of the COD concentrations. The suspended solids concentrations can also be either low or high and up to 20,000 grams per cubic meter. The nutrients content also changes considerably among the wastewaters. We can have streams with relatively high nutrients concentrations, such as those from winery or dairy industry. They will have both high concentrations of nitrogen and phosphorus. In the case of pulp and paper wastewater, it has high concentrations of nitrogen, but relatively low concentrations of phosphorus. And on the other hand, there are also streams with low nutrients concentrations, such as the textile industry. Landfill leachate, so the other external input, usually presents high concentrations of soluble inert COD, which is not removed in the plant and ends up in the effluent. And it can also contain high nitrogen concentrations, and sometimes a pretreatment is needed before it is discharged into the sewer. Here you have a couple of examples of the typical landfill leachate composition. You have one example corresponding to low wastewater concentrations and another one corresponding to high concentrations. If we look first at the COD concentrations, we can see that they can change between 1 and 16,000 grams per cubic meter. And we can also see that the COD is mainly soluble and there's only a very small fraction that is particulate. If we look now at the nutrients concentrations, we can see that for total nitrogen, the concentrations can change between 1 and 500 grams per cubic meter, and most of it is in the form of ammonia, while only a small fraction is actually organic nitrogen. The phosphorus concentrations are in general quite low and can oscillate between 1 and 10 grams per cubic meter. The total suspended solids concentrations can change between 20 and 500 grams per cubic meter, and normally at least half of it is volatile suspended solids, while the rest could be inert. So up until this point, we have seen two types of non-domestic wastewater. And here you have a summary of the typical concentration ranges for each stream, as well as the comparison with the domestic wastewater. We can see that for both streams, industrial wastewater and landfill leachate, the concentrations are much higher than those from domestic wastewater for COD, total nitrogen, and total suspended solids. In the case of phosphorus, the concentrations are a bit closer to those from domestic wastewater, but can still be higher. If we go back again to the scheme of the sewer and the treatment plant, we have dived into all the external inputs until this point, and now it's time to go to the internal inputs or internal loads in treatment plants. As mentioned before, these streams are produced internally in the plant. And to understand where they come from, the first thing that we need to know is how the treatment plant works. Here you have a simplified scheme of a wastewater treatment plant. First, we have the water line in which the influent or the wastewater is treated. The blue arrows indicate the water stream, and each block represents the main units that are needed for the water treatment. Normally, this treatment includes a pre-treatment, primary clarification, activated sludge, and a secondary clarification. The pretreatment and primary clarifier usually remove big solids from the wastewater. Then, the activated sludge system is a biological reactor in which bacteria remove the pollutants from the wastewater. And afterwards, the secondary clarifier separates the bacteria from the treated effluent. A sludge stream will be produced by the primary and the secondary clarifier, and this sludge stream needs to be further treated, in which is called the sludge line of a treatment plant. And here the sludge streams are indicated in brown. So, to treat the sludge, it first needs to be thickened. That means that part of the water will be separated and the sludge will reduce its water content. Then, the sludge is normally treated in an anaerobic digester, in which the organics will be biologically removed and biogas will be produced. The outlet of the anaerobic digester can be further treated in a dewatering unit, in which the water will be separated from the sludge. As you can see, water streams are produced at different points of the sludge line, such as the water that comes from the thickener, the outlet of the anaerobic digester, or the reject water after dewatering. And they usually have high pollutants concentrations and thus need to be treated. And this is basically what we call internal loads of the treatment plant. They are streams that are produced internally in the plant, they will be treated there, and they will contribute to the total load that will be applied to the water line of the treatment plant. And we have three main streams that contribute to the internal loads. We have on the one hand what we have just seen, water coming from the thickening and the digester supernatant, reject water from sludge dewatering, and also filter washing water. If we look first at the supernatant of the anaerobic digester, we can see that it usually constitutes a significant internal load, especially concerning ammonium. If this stream is not handled properly, it can lead to an overload of nitrogen, which can have a detrimental effect on the nitrogen removal efficiency of the plant. And here you have two examples of the typical concentrations corresponding to a case with low and with high concentrations. The COD concentrations can change from 700 to 9,000 grams per cubic meter. Usually, a big part of it, around 70%, is present in a particulate form, while the rest is soluble. The nitrogen concentrations can change from 1 to 800 grams per cubic meter, more or less. Ammonia is usually the main fraction of total nitrogen and can suppose 60–80% of the total nitrogen concentration. The total phosphorus concentrations can oscillate between 15 and 300 grams per cubic meter. And then the total suspended solids can oscillate between 500 and 10,000 grams per cubic meter. Normally, half of them are volatile suspended solids, while the rest is inert suspended solids. If we go now to the reject water from sludge dewatering, it usually has high concentrations of soluble material, including organics and nitrogen. For example, we can see in the figure that the average ammonia concentrations are around 1,000 grams per cubic meter, and they can oscillate between 600 and 1,500 grams per cubic meter. The organic nitrogen concentrations can oscillate between 1 and 200 grams per cubic meter, more or less, and suppose a much lower fraction compared to the ammonia concentrations. The average COD concentrations are around 1,000 grams per cubic meter, and the total suspended solids can be also high, with average values of 800 grams per cubic meter. Another internal input is the filter washing water. And this water is produced when different filters from the plant are washed. And here you have two examples of what the concentrations can be. We have again one case for low and one case for high concentrations. The COD concentrations can oscillate between 300 and 1,700 grams per cubic meter, and only a small fraction of it is actually soluble. The suspended solids concentrations can change between 300 and 1,500 grams per cubic meter. Normally, around half of them are volatile suspended solids, while the rest is inert. The nitrogen concentrations can oscillate between 20 and 100 grams per cubic meter. Most of it is in the form of organic nitrogen, and only a very small fraction is present as ammonia. And then the total phosphorus concentrations are usually low and can change between 5-50 grams per cubic meter. This stream has another relevant characteristic, that is high flows. If we want to treat it too fast, the flow to be handled by the plant can increase too much, and this can create problems due to high hydraulic overload of the settling tanks. And in some cases, it can even provoke an overload of suspended solids. Therefore, if we want to treat it in the plant, it is important to recycle it slowly, especially in small treatment plants. If we go back to the outline of this section, we have now completed all the points, and these are the key messages. We have seen two ways to provide an estimation of the loading to a treatment plant: the population equivalent and the person load. While the population equivalent is a fixed value, the person load can change. We have also discussed what is the municipal wastewater composition, the typical ranges, fluctuations, and the causes for these fluctuations. We have also seen how to calculate different ratios between wastewater components and its importance when we have to select the treatment processes. We have dived into the domestic wastewater substreams, being toilet, kitchen, and bath or laundry the main contributors for the wastewater. We have also discussed the non-domestic streams, which are mainly industrial effluents, and other streams such as landfill leachate. And finally, we have also seen which streams produced internally in the treatment plants can also contribute to the load that needs to be handled. And these include the anaerobic digester supernatant, reject water, and filter washing water.